All right. Good morning, guys, and welcome back. So, if you recall what we are treating in the previous class, we said something about instance-based learning, and by way of explanation, we looked into what the motivation behind instance-based learning and why it's actually called instance-based learning, right? And we saw some examples of instance-based learning methods. We saw locally weighted regression. We saw case-based learning. And then we saw what? The nearest neighbor, right? So, one of the things we discussed yesterday was the advantages and the disadvantages. That it is very fast is an advantage. But again, the cost is small, right? It's not an advantage in this case, but rather a disadvantage. Now, in today's class, we're going to explore some certain things in this class. So what are the concepts you're going to learn today? So today's class will be focused on K nearest neighbor, K nearest neighbor. All right? So after which we look into the distance weighted linear regression. How? It's actually not distance weighted linear regression. It's called distance weighted nearest neighbor. Okay? So distance weighted. Now I'm going to use NN for short, nearest neighbor. Okay? And then in here we look at the training algorithms. Training algorithm. I've used algorithm for short. Okay, fine. Followed by some terminology. So I think, we look at some terminologies here. Then we look into now locally weighted linear regression. Remember, this was distance weighted neural net, nearest neighbor. I kept saying neural network. And this is locally weighted linear regression. All right. So there's something, and then in K nearest neighbor, we might look into how we actually determine the nearest neighbor, and then the concept of Voronoi NOID diagram. Okay. So I'm going to put this in quotes, Voronoi diagram. Yeah, because it's not an algorithm, it's actually a kind of a concept, a pictorial representation of the sample space, kind of. Okay, that's a loose analogy. So if you look at this, something that comes to our mind is, what is KNN actually, and how is KNN different from Kmeans? Right? This is an obvious question which we need to address. So before we start, let's try to kind of differentiate between the two. So there we go, we have KNN, and here we have Kmeans. So in KNN, it is actually a supervised learning algorithm. So it is supervised, whereas Kmeans is what? Unsupervised. Unsupervised. Okay. Now, there is also something that is very different here. K stands for what here? K stands for what? So K in Kmeans stands for number of clusters. K equal number of clusters. Then K stands for what now here? Number of nearest neighbor. Nearest neighbor, okay? Closest neighbor. Neighbor. Okay? Now, application-wise, this is mostly used for classification and regression. Used mostly for classification and regression. And this is mostly for, you guessed it, for what? Clustering. Okay? That means here we need label data, right? And here label must be provided. Must be provided. Whereas here, usually labels are obtained by determining the number of clusters, not necessary. Now, in terms of estimating this, we know that this the number of k is estimated by, by using what we call what? By some distance matrix, some distance measure. Let me call it now measure, such as what? Such as what? Such as Manhattan, and your famous Euclidean, and another one which you call Minkowski. So I'm going to focus more on the Euclidean, right? And here you estimate k is estimated. Okay, did I overshoot my runway? You know, okay, the runway here, I'm talking of the section portion of the board. Anyway, you know what I'm talking about. So it's estimated by using what we call what? Elbow method. What we call elbow method. Cool. So I think with this we have set the pace for what we're going to do today, right? Because it's something that, you know, most students try to get confused about, right? When we talk of k nearest neighbor, they are talking about k-means. So be well informed that KNN is supervised, whereas k-means is unsupervised, okay? And then there we go, and I think with this, there's now a clear distinction, okay, between the two, right? So let's take some examples and then let's see how actually they differ from each other. Let's look at k-means, okay, which most of you always, you know, most of you encounter, right? So in k-means, we take the famous iris data set. So let me just take some example here, okay? So this is k-means, okay? And then for my KNN, I'll have something. So let's discuss k-means first before we get to the sample space of KNN. So in k-means, say I have some clusters of flower. See, I'm just drawing, okay? This is another flower, something is there, okay? Then another flower is here. Some flower is there. Some flower is there. Another flower is there. Flower is there. Flower is there, okay? So these three, maybe we call this iris setosa, iris veriscolor, iris virginica, right? Now a new species comes, maybe which lies here, right? So this is the new species. So to which cluster will this belong to? I would say it belongs to this cluster, right? Now this is a loose way of calculating the clusters, right? Because in most cases also we try to determine, please remember one thing, in k-means you have to decide the number of clusters in advance. And that we only decide by using what we call elbow method. So you might ask, how is the elbow method now different? Okay, or how do we actually estimate the elbow method? So the concept of elbow is there should be a bent curve, right? Like an elbow, okay? So the graph of the elbow method will look like something like this, okay, with some, some curve going up, and suddenly you will see this, okay? So where this starts bending sharply, okay, then maybe the number of clusters is 3, okay? So we now choose, okay, fine, this is it. But we are not going to look into k-means because that is not what we have to study in instance-based learning. Now you understood some basic concepts of k-means, that is revolves around what? Clustering, and revolves around what? Choosing the number of clusters by going through your what? Your elbow method. Now let's understand k-nearest neighbor. So k-nearest neighbor, one thing you should understand here is that k-nearest neighbor uses what we call what? Majority voting. So here uses what? Uses majority voting. So what is this majority voting now? Right? So if you look here and take example now, I have some shapes. Okay, let's say I have this shape. Remember this shape is circle, circle, circle. Okay, and then I'm just putting a grid around it. Okay. Now I have another shape here. Okay, yeah. Apart from circle, there is a triangular shape there. Okay. Remember there are 3 circles here now. Now outside here I have another triangle, maybe with some rectangular shape, square shape, and some rectangular shape, right? So, and maybe something that looks like a kite, something like that, right? And then this is, I'm just using this, okay, to give this, all right? Now I have a new instance which is like a plus sign, okay? This instance is to be classified, right, based on KNN. Pay attention now. So what KNN will do is, it says, see, majority, right? If I look at this grid, I'm talking of this grid, right? Which one appears more? Now I have only 1 triangle and 3 circles, right? So this plus will be assigned to the circle category. Now, therefore, such that, I'll write it here, such that this plus sign will be assigned to what? Circle category. Does that make sense? Okay, I think you're not able to see, but I just explained what I'm trying to do, okay? Now, this is when we chose the number, okay, the nearest neighbor to be 1. Nearest neighbor, okay? Now, if I increase this, let's say I'm considering this now, I'll come to this grid, right? So you see, here I'm getting, oh, okay. Okay, I made almost all of them equal. Okay, let me say triangle, obviously. So when I increase the nearest neighbor now to be 2, now what I get here is 1 triangle. Now let me count the one which has the maximum, right? The most frequently occurred shape. 1, 2, 3, 4, 5. In this case, the plus sign now will be assigned to the triangular shape, right? So you might say it doesn't make sense, right? Because plus and triangle, they are different shapes. Who cares? That is how KNN understands that, and that is how the algorithm works. All right, so before we look into the Voronoi diagram, let's understand the algorithm. Like, how does the algorithm look like? So the algorithm, K nearest neighbor algorithm is like this. Now you can actually frame the algorithm yourself, right? KNN algorithm. So the first step, so there are about maybe series of steps. Let's find out how many steps are there. So the first step in KNN says what? You determine the value of K, because you have to prefix it, right, before you even start running the algorithm. So you determine the value of K. Next, what do you do? So you calculate the distance between the new points, right? That is your what? Your test data and all the training data, right? So now, I believe by now you know the difference between test and training. If you don't know, please refer back to the previous videos. So now, the commonly used method, as we have already said, is what? Your Euclidean, your Manhattan, and your Minkowski. So what you do here is, you now calculate the distance between the test and training. Okay, so step 2. So can we say determine the distance between the test and training using either what? I'll start with Euclidean because we know that for sure. Euclidean, Manhattan, and Minkowski. Okay? So that leads us to step 3. Right? So in step 3, what do you do? In step 3, you now sort the distance, what? And you sort the distance and determine the K nearest neighbor based on what? What? Minimum value. So the essence of this is to minimize the class distance and maximize the inter-class distance. Okay, so what I mean by intra-class now, right? So I'm using class as synonymously with what? Neighbor. So let's say now in this, you sort this distance based on the one who has the minimum distance to the next neighbor. That's what step 3 tells you. So you sort this and determine what? The nearest neighbor based on the minimum distance. And determine the nearest neighbor based on minimum distance. Based on minimum distance. Minimum distance. Okay? So after that is done, what do you think will be the fourth step? Step 4. You've sorted it, right? So what do you do now? Now what you do, you assign that test data to the majority vote. Yes? See, now that you have calculated the nearest distance, you've sorted according to that. What do you do now? You assign that, right, to the what? The distance with what? The test data with what? The majority vote. So you assign, yes, to the what? To the majority vote. So you assign the test data. So you assign test data based on what? Majority vote. And then what do you do? I think we are done with this. So what do? You now give the predicted class, right? So basically you display the predicted class, right? So we say you return the predicted class. Fine. Now, this is kind of a generic overview of how it works, okay? Neighbor based on the minimum distance and stuff. But how do we actually do that now, right? So I believe from your high school, you know how to calculate the distance between 2 points. So since we are going to focus this, we are going to base this algorithm purely on what? On your what? On your Euclidean distance measure. So it's worthwhile investigating, okay, the distance, the Euclidean distance formula. Hence, let's take some 2 points. So assume, for instance, you are asked to determine the distance between 2 points. Say, now find the distance or determine, for instance, if you are asked to determine the distance, let's take this, the distance between A and B. Now, if I find the distance between A and B, I must tell you the coordinates, right, of A and B, right? Such that here I have A is maybe like I say 6, 4, and B, maybe I say 2, 3, right? So what does these coordinates imply? Now, these coordinates are just telling you that these are points in XY plane. So your coordinate geometry, you have your x-axis or your your x-axis or your abscissa or your independent axis, and you have your y-axis or your ordinate or your dependent axis. Now, if you look at it this way, here it is my x and that is my y. Simultaneously, I have another x there and I have another y there. So it makes sense now, it makes sense if I give them names. So this I call x1 and y1, and that I call x2 and what? y2. Such that the distance between these 2 points, if I represent it in a two-dimensional plane, it will look like this. It will look like this. Let's take some points now quickly. Now there are no negative values here, so I can represent everything in the positive axis. Now here I have my y, there I have my x. Now I take some scale. So anyway, 1, 2, 6, 1, 2, 3, 4, 5, and 6. 6, 5, 4, 3, 2, 1, with 0 being the center or the origin. 1, 2, 3, 4, 5, and 6. So I chose equal scale. Now, where is point A in this dimensional plane? So point A, it is 6, 4. So 6 is the first value, right, which is the value of x. So here I have 6. I trace it. There I get 4. I cut it there. So 6, 4. The next one is B. B is 2, 3. So 2 is my, sorry, I made it alter. 6 is my x, 4 is my y. That you should see. Okay? So here 6 is my x, 4 is my y. So that is the first point. Now the next is 2, 3. So 2 is x, 3 is y. 3, 2. Right? Now I've got these two. So what I will do, I will join it with a hyperplane now. Now here I'm talking of a straight line. I join it with a straight line. Now my question is, A is here, B is here. How far are they from each other? So that is the distance, right? Now, how far are they from each other? So by default, what comes to your mind is take the difference, right? And you are right. So what we do here is, if you say here x2 minus x1, whatever, so we normally say you can start with x2, you can start with y2, it doesn't matter. But by default, it is y2 minus y1, it doesn't matter. Now all squared, plus you now say x2 minus x1, all squared. Now watch this. Since we are actually doing this, okay, and we are squaring it, this will not minimize the error. Let's see. This we can calculate the distance by doing this much. Yes? But let's do this now. So y2 is what? y2 quickly. 3 minus 4. So you can do that. 3 minus 4 whole squared plus, now x2, 2 minus 6 whole squared. 2 minus 6 whole squared. Now, before this, simple distance measure says take the difference, right? So if I take the difference between those 2 points, what this boils down to is y2. Oh, no, you won't see from there. Ouch. So this boils down to y2 minus y1. Okay, this is done. Then plus x2 minus x1. Wait a minute. This is not the formula, but just wait. You see where I'm going to. This is the basic distance formula, between 2 points. That's what we can do here, right? Definitely. I want to know how far apart they are from each other. Now, why am I using that? Because I've plotted it in that two-dimensional plane. Now, my y2 is what? 3. y1 is what? 4. So if I say 3 minus 4, then I'm going to go into what? x2. So x2, I'll get 2 minus what? x1, which is 6. Now, if you look here, I'm going to get negative values. So watch here, minus 1 plus minus 4. What did I get? Minus 5. Now, can this distance between A and B be negative? No way. That is the reason why this is not the formula. Rather, the formula is we square this. Yes? We square that. Now, if you notice here, if I square this and that, what I'm going to get here is what? Quickly. I'm going to get 25, right? Minus 5 whole squared, I'll get 25. Yes? But you notice here, 25 now is very far. Oh my God. See the points. How do you tell me that they are 25 units apart? That's why, again, we put the square root. Does that make sense? Hence, if I do repeat the same thing, what I'm going to get here now is, I will square this, fine. I will square that, fine. Now, I see that this boils down not only to minus 1 now, but it has changed to what? 1 plus 1 squared is 1 plus, now this is what? This is what? Quickly, 16, right? So, this is what? 16. Remember, 2 minus 6 is minus 4 squared is 16. So, I will now get what? Square root of 17. Okay? Units. And in this case, it will be like what? 4 point something, maybe let's say 4.2 units. And this made sense because if you check here, if you check clearly, you will see from 2 to 6, just see, 3, 4, 5, 6 is around 4 units, not 5. Got it? Now, but you see why it is also not exactly 4, because this is not on this, just what? It is not like this. It is not exactly perpendicular, it's not exactly parallel to this x plane, okay? It's not parallel exactly to this x plane. And neither is it exactly perpendicular, right? So it's kind of tangential to it, right? So it made sense now to say that the distance is 4 point something units. So if you punch your calculator, you get the exact value of root 17. Now that you understood the concept behind Euclidean distance, you use that to calculate what? The Euclidean distance between this, and then you assign it to the neighbor, nearest neighbor. Now, the training algorithm will look like this, because we said something, no? After you determine the distance between the test and the training, using either the Euclidean or whatever, so that means before I give the test, I must have done my training. So let's look at the training algorithm, how it looks like. Fine. Okay, that's where we are now. So, algorithm over. So we are now here. KNN. KNN for discrete valued. So for each training example, call it f of x, comma. What do? You add the sample or the example to the list of training examples, right? Add lists of training examples. Then after this is done, what do you do next? You perform classification. Then you perform classification. So what does it say when you do this? So you now assign, right, some instances which are meant to be classified. Yes? And then you return the one with the what? Maximum. Because we said something here that this works on what? The majority voting. Okay? That's why you'll be seeing the word, the keyword, the function argmax. So we now say let x1, x2 to xn be sets of what? K instances from the what? Training example. That is nearest to what? That instance, right? S of what? Q. So we now say here, let x1, comma, x2, comma, down to xn be what? Be what? You guessed it right. Be what? K instances from what? Be K instances from training examples. From training examples that is what? Nearest to x. That is what? That's nearest. That is nearest to what? X of what? Q. Okay? That's nearest to x of Q. So what do? Now you return the one which has the majority voting. Yes? So you return what? What do you return? The function should return what? The instance that has the nearest what? Voting. So that makes sense. So we want to classify this instance, right? F of what? X of Q is the new instance which we want to classify. So we want to classify this now, right? So we have to return what? Maximum. So maximum is argmax. Minimum is argmin function. So argmax in Python, okay? Of what? Of what? Quickly. The training examples, right? Now, such that, look here. We need to compute the partial derivatives of what? Those instances, yes? And we know that it can either be classified rightly or it's classified wrongly. So if it's classified rightly, we say it is what? 1. And if it is classified wrongly, we said it is what? 0, right? Now, we will now have this, okay? Argmax of, and remember we are going to sum this over, right, those new instances. So that's why we have summation of I equal what? 1 to k, yes? Of what now? We find the partial derivative of this, yes, of the function with respect to some constant. So this is the constant. We're going to find the partial derivative of this function, yes? Fine. And we know that something will hold true. We now say where this partial derivative, where partial derivative of that, okay, will be equal to what? 1 or 0 otherwise. If we compute this, this will return 1. That means they are same. They belong to that same neighbor. If and only if A is equal to B. So what happens when they are not equal? Otherwise, 0. Otherwise, 0. Return what? 0. This made sense, right? Because when we check this and computed this, right? If that instance exactly, is the same with the nearest neighbor, then we return true. Otherwise, we return false.